Hi, welcome to EC&M Tech Talks. This is one video in the EC&M Tech Talk series where we go in and we explore different types of electrical equipment. We take a look at its theory of operation, maybe a little bit, how it works, how to troubleshoot it if need be. And then we also try and take a look at the code requirements as well for its installation. That's what we're going to do today with this electromagnetic motor starter. Well, anyway, EC&M Tech Talks is brought to you by EC&M Publications, tremendous magazine, electrical construction and maintenance. If not already, you need to go to ecmweb.com. That's ecmweb.com and look up in the upper left-hand corner, and there's a drop-down menu. And the very first item there, it says premium content. You need to sign up for that premium content. First of all, it's free, but it does give you lots of information. In addition to these tech talks, there's other videos, webinars, interviews, lots of articles, information for you that can provide you some of that basic set that we need out in the field, as well as some advanced information as well. So anyway, let's go ahead and get started. I'm Randy Barnett. I am an electrical safety instructor, journeyman electrician, safety professional, electrical inspector, and so on. Anyway, that's a little of my background, industrial type work primarily then. Today, we're going to be talking about the electromagnetic motor starter. We're going to start and we're going to talk about what it is, what it's supposed to do in life, how it works. Then we'll take one apart. We'll get our old trusty screwdriver. We'll pull this baby apart and take a look on the inside. We'll set up a meter and see what we need to do in order to troubleshoot this thing. Once we understand how it operates and how we can troubleshoot it, what it does for us out in the field, then we can take a look at the NEC requirements for motor controllers as well. All righty? So let's get started. What is this thing then? This is two separate devices, actually. This is a starting contactor up on the top. It's a relay. It's an electromagnetic relay. I energize a coil of wire up here that pulls in a magnetic bar. When I pull in that magnetic bar, it closes some contacts. So current flows into the top, through the contacts when they go closed, through the bottom section, which is called the overload relay, and then from there, T1, T2, and T3 down here, out to the motor. Nothing else between here and the motor typically. So anyway, the top portion then is called a starting contactor. It's a special purpose relay whose contacts are designed to start and operate safely an electric motor. I can use a wall switch. It has contacts in it. I could use just a regular old double pole or whatever switch and start and stop a motor, I guess. You know, the problem is when I shut off that motor, that electromagnetic field that's so strong inside of the motor, those magnetic fields collapse back into the windings and cause current flow to flow back into my switch. That current that flows creates a big arc across those contacts when they open up. It's called electromagnetic induction, or what we often call that inductive kick. Okay, so that inductive kick can burn up my contacts. I don't want to do that. So the code says, hey, I can't use things to start and operate motors unless those contacts are properly sized to interrupt that amount of current flow. So this particular starting contactor or relay, in other words, is a starting contactor because it's designed to start and operate. We're going to find a 10 horsepower, 460 volt motor. The bottom portion is the overload relay. When I combine the overload relay with the starting contactor, the entire unit I call a motor starter. Sometimes we'll also have a disconnect switch associated with some overcurrent protection when we start talking about combination starters. But anyway, so we're looking at the electromagnetic starter right now, the controller that's going to start and stop the motor for us. The overload reset button. Okay. I have heaters down below. We'll take a look and see how they operate. And let's go ahead and we'll pull this baby apart, see what it looks like on the inside, how it operates, both the relay section on the top and the overload section down below. And we'll do a little basic troubleshooting on it, show you a couple of the things that can typically go wrong with it, put a meter on it, and then we'll take a look at some of the code requirements and applications as well. All righty, so let's pull this thing apart. So let's start by taking a look at our NEMA motor starter. Once again, a little bit better close-up view of it. you can see it is labeled a NEMA size 1. A NEMA size 1 is designed to start and operate a 10 horsepower, 460 volt motor. These numbers are pretty small the way they're printed on here. But anyway, it says 200, 230, 7.5 horsepower, 380, 460, 575 volts AC, 10 horsepower, okay? And 600 volts AC max. Now that's the rating of the contacts. The rating of the coil down here, it says is 120 volts. So I'm going to apply 120 volts control power through my coil. I'll bring my coil wire or my 120 volts in, come through my overload relay, the contacts in my overload relay, and come up to my coil. That way, if any of my overload relay contacts open up, it will de-energize the coil of wire. Magnetic pressure will pull the spring open. Anyway, so the power comes into the top, L1, L2, and L3. And I've got the top terminals up here. Of course, everything is disconnected right here, but that's where my incoming 460 normally would go in. And then coming off the bottom, this would be T1, T2, and T3. And there's generally nothing else between there and the motor. That's it. I go directly to my motor from there. Okay. This is my reset button to reset the overloads should one of those resets trip. So let's pull apart and take a look on the inside. First, we'll see the top portion. We'll see the starting contactor and see how this operates. So this is my coil of wire. I energize and de-energize this coil of wire. Let's pull the coil out. There's my coil. Sure enough, my coil comes apart. And I supply power to the coil. When I energize this coil of wire, the electromagnetic field pulls in this lever. When it pulls it in, notice what happens. This middle portion drops down, pivots downward. When it pivots downward, and by the way, there's a little white tab right here. I can also push by hand, okay? And I can manually close the contacts. But when that little white tab is pulled in, that bar is pulled in, this bottom section pivots down, and that's my contacts down below there. So let's take a look at those contacts. So I remove the top portion, and these are my movable contacts in. I'll roll it over so you can see them. Here's my movable contacts. As I pull that little white lever on the inside, those contacts are going up and down. And they're in pretty good shape, actually, look like right now. Haven't been used very much. But I can replace those if need be. And those are my movable contacts. Now, the stationary contacts are on the inside and the back side of this. There's my stationary contacts back there. They can also be replaced as well. So I have the top contact and the bottom contact, right? So the power comes in L1, L2, and L3 through my contacts and on out to my overload section down below. Okay? Let's pull off one of these overloads. These are thermal overloads. They're actually what we call solder pot types. So this is what we commonly refer to as a heater element. It has solder on the inside of this little chamber in the back. There's a little cogged wheel right here that I can't turn right now. And I can't turn it because the solder is cold on the inside. If I were to melt the solder on the inside, then that wheel would turn. If that wheel were to turn, it's sitting up against spring pressure on a little thermal, on my little, contact overload bar right here. If I move this, once it's reset, and if that little wheel turns, then that little bar drops out. And when it does, that bar moves, that opens up contacts. In fact, if any one of my 3 thermal overloads operate, the solder melts in them, the contact bars open up and the contacts are open in the contact block on the side. And as we said, that de-energizes the coil. So the things that will go bad typically inside of a motor starter, coils will burn up and I may have to replace a coil. So just a coil of wire and an epoxy. All I can do with that is replace it if need be. Contacts will go bad. I can dress and clean contacts. I'll find information in the NFPA 70B standard, the recommended practice on electrical equipment maintenance on how to do that. And then overloads will go bad as well. And I can always replace my overload elements as need be. Okay? So how do I know what size overload goes in? Article 430 in the National Electrical Code will tell me how to properly size my overloads, given certain characteristics of the motor and the operation of the system and so forth. So anyway, that is how our motor starter operates. Now with our motor starter reassembled, some of the basic troubleshooting techniques should make sense to us, that we understand what and how it operates on the inside. So the meter is set up to read resistance, of course, what's definitely the preferred way to troubleshoot. And we always want to make sure that our circuits are de-energized before we ever go into troubleshoot reading resistance. So let's take our meter and see maybe a couple of basic checks that we can do then. First, I'll make sure my meter works properly on resistance by touching my test leads together. And some things that I can do. I can check for continuity through the entire circuit. I could take, if a contactor like this, starter, if I take and I put one test lead up here, say on the top, let's put it on L1. So I put it on my incoming L1 power. Then I take the other test lead and I put it down here at T1. Right now, with the contacts in the open position, I do get OL, open circuit, on my meter. However, if I take and I push down this little white tab, as we saw before, that will close the contacts. And so if I close the contacts, well, my meter goes to 3 ohms. And I can do the same check, and I'm just checking for continuity. I'm not checking for an actual resistance value, but I'll go from L2 to T2 and close my contacts. They're open right now. Sometimes those contacts will burn shut on you. And if I get any resistance right now, I got a problem. It's time to dig into those contacts and probably replace them. I can go ahead, push it down. I've got 10 ohms, 10.4 ohms. But once again, I've got continuity from L2 to T2. And I can also go ahead and check from L3 to T3 and make sure that I have continuity. Okay. So all 3 of my contacts are working right now. All 3 of my overload heaters are working. I've checked for a complete path of current flow. I can also go ahead and check if I suspect I'm having problems with my coil. I could lift one of the leads, or in this case, we've already got both lifted on my coil, and I can read the resistance on my coil. What should it be? I don't know, as long as I've got some. It's not reading OL, and it's not reading 0. Right? So I've got 31.8 ohms. I would have to say that that coil of wire is a good coil. So those are a couple of quick basic checks that you can do on a motor starter that can help you out in the field when you're troubleshooting. Right? So next thing, let's move to the National Electrical Code and see what the NEC has to say about motor starters then. That is the electromagnetic motor starter, or what we refer to as the controller, because it's going to start and stop the motor safely. A couple of additional things, of course, it does provide the overload protection that we need. That if the motor draws too much current, it'll protect the motor. That's what the overloads are designed for. Also, another term that you'll hear is low voltage protection. This is where when the motor, if I lose power to the motor, obviously the coil drops out. In fact, it'll start to chatter at around 70% or so of its rated voltage. But if the coil drops out, contacts, of course, will open up. And then the motor is protected against that low voltage situation, low voltage protection. If I want to restart the motor, I have to re-energize a coil of wire then, however I choose to do that. Different combinations. One of the most popular types of ways now, and certainly an important application for starting and stopping motors, is the use of the variable speed drive, or adjustable speed drive is what the code calls it. That's another whole topic. we'll get into that in the electronics one day and what we do with adjustable speed drives and so forth. So anyway, let's get back and let's take a look in the NEC, National Electrical Code. I'll use the 2020 version since it's the most current, the latest. And we'll take a look at the requirements in Article 430. Article 430 is motors, motor controllers. And so let's take a look at Article 430. What I'm going to do is I'll put a couple of items up on the screen for us so we can take a look at it. And then I'll go through some items in the code book. So now we're into Article 430 of the NEC. Article 430 is under motor, or it is motors, motor circuits, and controllers then. A few things that I want to point out to you in addition to what's up on the screen. First of all, that image over on the right-hand side that you see, that is a typical motor controller then. So over on the left-hand side, here's my electromagnetic motor starter. The power comes in. This is the inside of an MCC motor control center bucket. So the power comes in from the back side to the top of these stabs. When the disconnect switch goes closed, and right now you can see the knife blades are open. So to operate those knife blades, I throw the handle on the right-hand side. It's in the off position right now. If I throw it to the up position, then it will turn on. The knife blades will go closed, and then I would have power to these fuses. The 3 fuses, of course, provide my short circuit and ground fault protection. I come off the bottom of the fuses, and the conductors go around and come up to the top of the motor starter. So that's L1, L2, and L3 coming into the top. Here's my coil of wire on the front and my overload section down below. Off the bottom of the overloads, I run to T1, T2, and T3 over here to the motor, and doesn't look like we have a motor connected right now inside of this MCC cubicle. Okay. Now, some important items then out of Article 430. In addition to what you see up on the screen, first of all, 430.8 talks about markings on controllers, and I'm not going to review any of that. You can take a look at that as you need to. But anyway, so it does, there are required markings in. The 2 important parts, part 7 is motor controllers, and 430.81, okay? And tells me, well, first of all, I have to have a controller for each motor. It says, well, it says require suitable controllers for all motors. I'm sorry, is the actual terminology there, okay? And then it goes on down, and it divides it between the different types of motors and how we stop those motors. So anyway, that's 430.81. The big thing out of that, I must have a suitable controller for all motors. In our case, we're using our electromagnetic starter. So 2 important parts out of this article are part 7 on motor controllers. And then I want to take a look at part 9 on disconnecting means. Part 7 on motor controllers, 430.81 tells me I have to have a motor controller for all my motors. That's what it says. I have to have some type of controller for all my motors. And then it breaks it down into stationary motors and portable motors and so forth. But take a look at 430.82 has to do with controller design. In subsection A out of 430.82 says each controller has to be capable of starting and stopping the motor it controls and capable of interrupting the locked rotor current of the motor. That's the maximum amount of current that motor is going to draw under operation then. And so important concept there, we've got to have the controller. It's got to be suitably sized and designed for our particular application. Also, let me point out 430.83 talks about ratings, and subsection A, some general information. To me, it's kind of that electrical common sense thing. The voltage rating on our controller, the application voltage, cannot be lower than the horsepower rating of the motor. That's true. Our motors have to be sized in order to, or excuse me, the contacts have to be sized properly inside of that contactor. So we saw the example of a NEMA 1 size starting contactor then. Now, if you jump over to part 9, the disconnecting means, that's that disconnect on the right-hand side. That's more information and probably some more relevant information to you when we get involved in the installation out in the field. So part 9, specifically 430.102, has to do with the location of that disconnect. So what we found out, or what we find out, is that each motor and each controller must have a disconnect. But we also find out in this article that one common disconnect can supply both the motor and the controller. Also in part 9, 430.102 tells me the location of that disconnect. It talks about the location, A for the controller and B for the motor. 430.102. So all disconnecting means, it says, shall be located in sight from the controller location. And if I go back to Article 100 and look up that definition for in sight, it means that it has to be visible and within 50 feet of the equipment. And then you say, oh, that's what we call the general rule. Anytime an instructor says the general rule in the code, be aware that means there's maybe some exceptions, or there probably is. And certainly there is for the location of that disconnect. So you want to take a look at that as well. 430.103 talks about the operation of that disconnect. It has to open all the ungrounded supply conductors and so forth. And at least one of the disconnects for the motor or the controller must be in a readily accessible location, right? Quite a bit of information then in part 9 as you graze through that. So that is our motor controller then. That is what it is, what it does, what its function is in life. Some basic tips on how to troubleshoot it. We took a look at how it operates, and we looked at some of the code requirements as well. Obviously, there's a lot more to it. So study your code book, okay? Learn more about motor starters, control circuits, and so forth. Main thing is you work safely out in the field. We've packed a lot in today, and I want to thank you for attending and hope you enjoyed it, got a few items out of it. Remember, this is EC&M Tech Talks. It is brought to you by EC&M Magazine, which is part of the portfolio of Endeavor Business Publications. Main thing is that you get out there and you work safely in the field. Make sure you sign up for the premium content. And we'll see you next time when we're going to talk about grounding and bonding, but not just Article 250. We're going to get into some of the specifics I think you'll enjoy, applications and so forth, some of the nitty gritty on grounding and bonding maybe, all right? We'll see you next time. Thanks again and work safely.